Hey folks, how you doing? We want to talk about chapter 6 today. This is part A of bones and skeletal tissue. So I want to discuss this and talk about this here. Now looking at bone and skeletal tissue, we first look at 6.1. So if you're following with your book, 6.1 is where we're going to start. And we are talking about skeletal cartilage. Okay. So again, when we look at initially fetal development, when we're talking about fetal development, initially at the beginning of life, we find that um, the human skeleton is just made up of cartilage. And in fact, it begins as cartilage and then gets replaced by bone as we go from fetus to late fetus in vitro in the mother's womb. And then outside of the mother's womb, we still continue to grow and replace cartilage with bone. Um, and even at the ends of those bones, we still have flexibility. We still have cartilage there in place. When we have joints, for example, is a place that you still find cartilage occurring inside the skeletal system. Okay. So looking at cartilage, since that's the beginning of really looking at the tissue that makes bone itself, it is highly resistant. It is moldage cartilage, that tissue that is made up primarily of water, does not have any blood vessels, does not have any nerves. And so we use this word here, and I'll go ahead and highlight this word here, perichondrium. Okay, perichondrium is a layer of dense connective tissue that surrounds the cartilage, very much like a girdle. So this is actually where we start to see cartilage forming and first starting to see this dense layer of connective tissue that covers the entire cartilage itself. Okay, its function: resist cartilage from expanding outward, and this is an area that contains blood vessels that are really important for nutrient delivery to the cartilage itself. Now that blood vessel system is not a direct system to the cartilage, it actually is an indirect system, so nutrients and oxygen get fed to this layer, the perichondrium, and then indirectly it feeds then the nutrients and the oxygen that the cartilage needs to continue to be healthy and to continue to perform its function. Okay. Now the cartilage is made up of what we call chondrocytes, and these are cells, and I'll go ahead and use our highlighter here. Um, cells encased in a small cavity that we call lacunae. Okay, lacunae within this matrix. And so we use matrix again to describe this connective tissue. Cartilage is a connective tissue, in fact. And so we see the cell here, chondrocytes, encased in a lacunae, and these lacunae are actually encased or found within this, this jelly-like matrix. Okay, so when we look at cartilage, we see that there's actually three different types of cartilage that you find in the body. We'll look at the locations here as well. But the first one we talk about is hyaline cartilage, right? Hyaline cartilage. Hyaline cartilage, by definition, provides support, flexibility, resiliency. We find this as the most abundant type that you find in the body. Okay, does only contain collagen fibers. Okay, and you find this in places like the articular capsule, the articular joints, the costal ribs, for example, those bones and at the end of those bones, the respiratory system, and in nasal cartilage, the tip of your nose. So just a quick exercise I like everybody to do. If you feel your nose from the end, you'll notice that it's, you know, somewhat squishy, somewhat flexible. You can move it back and forth, but as you grab the bridge of your nose and go all the way up, you'll feel a point there, in fact, where the cartilage meets bone. And that is actually where you find the cartilage ending and your bone, your nasal bone, beginning. And so we look at this to kind of describe this type of hyaline cartilage, and you can feel it does give support, does give flexibility, does give resiliency, because if you can move that around, in fact, it will go back to the normal location and wouldn't actually stay in one location. So hyaline cartilage, right? Elastic cartilage, similar to hyaline cartilage, but does contain elastic fibers. So it does have, in fact, collagen fibers and elastic fibers interweaved in this cartilage. And you find this really in the external ear and in the epiglottis. So two of which are really important places. The external ear is all your, ear that you pull that you can feel on the outside of your body. And then also your epiglottis is a type of elastic cartilage that you find in the digestive system, the respiratory system. And what it does is it actually is a divider between the respiratory system and the digestive system. Acts as a little flap, if you will. And that flap actually, when you swallow food, will close actually the trachea that goes to the respiratory system, to your lungs, in fact, and will allow food to pass through into the esophagus and water into your stomach. If you did not have that epiglottis that is actually pretty flexible, what we have, is composed of elastic cartilage. As we eat food, it would travel into the lungs, so food would actually aspirate. We call this aspiration, but fall into the lung tissue. So, really important function of the epiglottis. And the fiber cartilage, think of the word thick. I'll go ahead and highlight that word, but think of the word thick there, because it is actually pretty thick collagen fibers. Okay, because they're very thick, okay, it has a tremendous amount of tensile strength. Okay, so it does, in fact, change the color here, does in fact have a tremendous amount of tensile strength. This actually resists a tremendous amount of force applied to this actual cartilage. Is very evident where this is found, because it does participate in a great amount of stress. If you look at the meniscus, which is the disc of cartilage, fiber cartilage between the knee, between the fibula and the tibia that make your knee. So a tremendous amount of force from the top of your body, your weight and your force, and the bottom of the leg below the knee. Okay, this meeting ground would be where the meniscus, or the disc that's fiber cartilage, tremendous amount of force there. And you also find this in the vertebral discs. Okay, the cartilage in between your vertebrae, right, your backbone, if you will. So we see both of these places hold a tremendous amount of force, and because of which they're made up of fiber cartilage. Would make sense logically looking at that. Okay, so this figure, figure 6.1, okay, is a indicator. It's a nice figure to look at when looking at the different types, again, of cartilage that you find in the human body. So there's your cartilage. I'm highlighting all that area right there of your three types of cartilage. But these colors represent, in fact, the three different types of cartilage. So I believe it's indicated with a nice blue color, a green color, and somewhat of a red color on the figure itself. And you can see these places where you find hyaline cartilage, elastic cartilage, and again, fiber cartilage. Okay. And so when we look at actually cartilage, we actually start to look at the growth of cartilage, because again, we really start at the fetal development stage, or the fetus in our lifespan, and we carry on through that lifespan. We see the cartilage increasing and changing, but in fact, cartilage does grow even past, let's say, adulthood. Does increase, and does grow, and it will continue to grow. But that growth will actually slow down after a while. So once you get into an elderly age, then it starts to slow down. Okay, but cartilage actually grows in two ways here. We call this appositional growth and interstitial growth, right? Appositional growth and interstitial growth. Appositional growth, you actually have the cartilage forming cells in the perichondrium. Okay, they are the ones that actually secrete matrix. Okay, and they secrete that against the existing cartilage. So we see new matrix being laid down on the surface of the cartilage. And in fact, the perichondrium is the one that actually makes and secretes the matrix that we see in cartilage. Okay, interstitial growth come from another cell. We call that cell chondrocyte, and those chondrocytes, in fact, that are the cells within cartilage divide and they secrete new matrix, and they expand the cartilage from within. So you see two growths or two types of synthesis of cartilage, one being from the perichondrium, okay, and then the other one being from chondrocytes internally into the cartilage. So we see these two different cells creating then cartilage and then adding that cartilage to actually cause growth of the cartilage. Okay. And so when we look at this figure, excuse me, this slide here, we talk about calcification of cartilage. Okay, so we use this word calcification. Okay, so what we're seeing here is that cartilage is actually being calcified. We're actually adding a mineral that we call calcium, Ca2+, right? Calcium. And calcium, writing my nice little 2 there. Apologize about my penmanship there. I'm using a mouse, so it doesn't really help me out too much to use a mouse here, but we see calcium, abbreviated Ca2+, right? Calcium. The mineral calcium actually can be added to cartilage, creating this hardened cartilage, right? This hardened cartilage. And what we want to have is hardened cartilage as we grow older. So as we go from our youth into adolescence, we want that cartilage to be somewhat hardened, a little bit stiffer than normal. But we don't want to have that cartilage being stiff throughout the whole body, but in major places that we use to flex and for movement. Okay, so we want to have it, you know, still flexible, but we want to have it strong too, and that's the two key things: make it flexible, but also make it strong. Okay, so here's our functions of bone. So there's 7 functions of bone, and we see 4 here, right? So the first one is support. So we know that bone supports things, right? Supports our body, supports our organs that are found in our body. That's one big thing. That one's an easy one to understand because logically, bone holds things up, supports stuff. Yeah. Protection, right? We see this really in the as very evident. Great example, right? Of in the brain, we've got this big, you know, cranium here holding the brain inside. Big protection kind of barrier. Spinal cord does the same thing. Our vertebral cavities, the spinal cord holds the spinal cord. The spinal cord is held in the actual spine, the bones and cells, and organs, right? Great example of that is the heart, right? See the heart getting held inside this rib cage, holds our, you know, heart inside of itself. Big kind of cage protecting then the heart, right? And the lungs themselves. Movement, right? Movement's a huge, you know, term there, a huge function that enables us to do many things, many tasks. Movement. And bones help us to contract our muscles because our muscles are actually attached to bone in many places. And by moving the muscle, contracting the muscle, we're moving bone. When we move bone, then we create movement, walking, running, sitting, standing, writing, sign language. This is all because of movement, right? Bones are a direct function of that, right? A function for that. Minerals, right? And growth factors, 2 of which are found in bone themselves. Minerals like calcium, as I mentioned, phosphorus as well, and growth factors. There are several chemicals that actually participate in growth. We usually think of growth in A&P, not just growing in size, right? Growing taller, growing wider, bigger. But we also talk about cells growing, increasing the number of cells that you have for a tissue, for example. That's considered also growth as well. And those growth factors, many of them are found in bone tissue themselves. Blood cell formation, right? We know that, for example, and you might not know this, right? But it's a very, very interesting to note that we actually grow our blood cells in bone itself, in bone tissue. And there's a particular place in bone tissue we call red bone marrow, found in certain bones. And in that red bone marrow is where we actually produce blood cells. Now these are your red blood cells and your white blood cells, so both of which are extremely important for sustainability of life, for our life to be what it is. So we call that that term hematopoiesis, okay? The forming of blood cells, and we actually form these continuously. Now we can form them in different rates, different amounts, and because we do that, we see the body changing. Because the body changes, we adapt to the amount and the volume, for example, of red blood cells and white blood cells that we produce. But hematopoiesis occurs in bone itself, so a very important function. Without bones, you would not have as much blood cell production. Here's an interesting one to note, right? Triglyceride fat storage. Triglyceride fat storage is a place, is actually where we place a lot of our fats inside of our bone tissue. And there, we're going to look in just a second to show you the actual triglyceride storage, where we find fats in our bones. Okay, we have those in bone cavities, but fat can be used as an energy storage, right? It's a place, for example, to store this energy that's held in these chemical bonds that we know to be fat. When we break those open, we can actually burn, or we call it burning, but it's not, has nothing to do with fire. We talk about breaking bonds and creating energy, and we can actually create energy from fat, and it's a great place to kind of stick that in there. One of the side benefits of that is that if you actually fill up the bone cavities with fat as opposed to, let's say, more bone, you actually lighten up the bone. You make the bone lighter. Because you make the bone lighter, the bones can be moved more easily. And so that's a neat side effect of actually putting fat into the internal cavity of bone versus complete bone itself. You know, the bone being, you know, let's say humerus bone, right? Arm bone. Being completely filled with bone would make the bone twice or 3 times as heavy as it is now. So imagine yourself, you know, looking at an entire skeleton being twice as heavy as you are now. Would be a tremendous amount of weight to move with your muscles. So we lighten it up, and the way it's kind of engineered is that we lighten it up and we put fat, you know, we make them empty and we fill it up with fat. So just an interesting side effect, positive side effect of having bone cavities and filling up with fat. And lastly, we have hormone production. And in fact, bone tissue does create hormones. They do make hormones. One of them being osteocalcin. Okay, osteocalcin is actually made by bone tissue, secreted by bone tissue, and that actually helps regulate insulin secretion, glucose levels, and metabolism. Really important things, all have to do with actually energy usage, right? Insulin secretion is a hormone. Okay, so insulin is a hormone. This helps regulate that hormone, and that hormone is responsible for bringing in sugars, sugars in our blood into our cells. So which is a really important thing to have when you want to make sure that cells are fed sugar, because sugar is really important for cells to actually use as energy as well. And so when we talk about glucose levels, that's the level of sugar, glucose, vis-a-vis glucose, simple sugar, inside our blood. And that all has to do with metabolism. If you remember that word from chemistry, from biochemistry, metabolism. The series of breaking and making bonds in a given time is called metabolism, right? Okay. So we classify bones in different ways, but one of the main ways we classify bones are based on location, right? We're looking at location. And so we can divide bones based on location, and they fall within the axial skeleton or the appendicular skeleton. Okay, the axial skeleton basically is a, you know, if you look at the axis of the body longitudinally, up and down, and the way I've always memorized it, if I took my, you know, hand like this and Pretend I drew a line right down the middle of my body. Anything it pretty much touches is all considered axial. So that's considered, the skull is considered that, the vertebral column is considered that, and the rib cage. Okay, all part of the axial skeleton. The appendicular skeleton is really easy to memorize or to know. Is any of the bones that belong to the upper and lower limbs. Okay, upper limbs meaning, your arm, including your shoulder bones. Okay, we call these girdles, by the way. Upper girdles and lower girdles, all your, your leg bone, your feet bone, your, shin bones, your, hip bones as well, your coxal bones. We call these coxal bones, but the hip bones as well. And this is, all considered part of the appendicular skeleton. All right, so before we, on the next slide, just want to make sure that you know there's 206 bones in the human skeleton, right? 206 bones. Does anybody know, if you can think of this, what is there are 3 smallest bones in our body? Where are they found? Those are found actually in the middle ear. Okay, so this would be the outer ear, your ear canal. Remember the cerumen, right? The earwax that's getting made by cerumeous glands in your ear. So when you hit the eardrum, from the eardrum, behind the eardrum, there are 3 smallest bones in the body, and those are part of that 206 bones, smallest bones in your body. Just to kind of side fact there, right? Okay. Again, looking at this, we look at this figure again because not only does it show the cartilages, it actually shows you, and I'm going to circle this, the bones of the skeleton. What falls under axial and what falls under appendicular. And the axial here in this figure is anything in this dark tan brown color, and then anything in the light brown color is your appendicular, right? So you also see this in this figure. So I decided I'd put that again to show you that part. Okay, we also classify bones by shape, and there are 4 major shapes that we find in the body. One being the long bone, or types of bones that we consider long, right? Short bones. Okay, and we'll see the other 2 in just a second. So let me talk about these, and then we'll go to the next slide. But the long bones are usually considered bones that are longer than they are wide. So if they're longer than they are wide, they're considered long bones. Okay. Most of your limb bones are long bones. So we talk about limbs being, humerus, radius, and ulna. Even your carpals, metacarpals, phalanges, these long, bones here of your hands, those are considered those. Your femur, which is your thigh bone, and your shin bones, the tibia and the fibula, considered long bones as well. Short bones, they're cube-shaped bones. You usually find those, for example, in the wrist, okay, and the ankle, okay, wrist and the ankle. So these are considered cube-shaped, square shape, if you will. Those will be found, for example, right here. These are all your wrist bones there. So you consider those all wrist bones. Now the longer ones here are your carpals. Those are long bones. But this set of bones here that you would call wrist bones, and there's several here, and the same in your ankle, those are considered short bones. Okay. A type of short bone that we see that's very unique, it's a unique shape, is called a sesamoid bone. Sesamoid. Comes from the word sesame, because it actually looks like a sesame. And this is a bone, for example, that you found within a tendon. We would talk about, for example, the patellas, the prime example of a sesamoid bone. It's found embedded into a tendon, and in fact, that's how your kneecap, this is the patella is the kneecap, how the kneecap is positioned on the knee itself. And if you were to look at it, if you were to take it apart and look at it, you would see it looks like a sesame shape. Okay. Flat bones, right? Just as the word indicates, flat bones are nice and thin, nice and flat, if you will. Okay. They're usually slightly curved, so you can see flat bones being curved. Okay. So when you find, for example, the sternum, which is your breastbone, It's bone that runs kind of right here, it's your breastbone. Okay, that'd be the sternum. It's a flat bone. The scapulae, right? That'd be your shoulder blade, if you will, right? Shoulder blade. Your ribs was a great example of a flat bone, and most of your skull bones. And when you look at skull bones, you know, front skull, back part of the skull, these are your flat bones. Even though they've got a curve and they might be rounded, still considered flat bones, right? And the last one, irregular bones. Shapes that don't fall in the other three is considered a irregular bone. The two big examples here are vertebra and your hip bones, right? The vertebrae and your hip bones, right? Those bones that form the spinal cord and those bones that form the hip. Okay, so just a side note, the hip bone, we know to be coxal bone, that's how you pronounce it, coxal bone, is actually two bones in one. So your hip is not one entire bone, it's actually two bones in, you know, making one hip, if you will. Okay. So here we see in this figure, you know, all of your, you know, your classifications based on shape, and they give you the four, you know, the four examples of each type. Okay, so we consider bone organs because they have many different types of tissue. Many types of tissue, more than two types of tissue that share a common function is considered an organ, right? And so bones are considered an organ itself because it has many different types of tissue. So not only does it have bone tissue, we call this osseous tissue, that's how you pronounce that, osseous tissue, but you also have nervous tissue there that make up bone. You have cartilage, which is connective tissue. You have a type of connective tissue called fibrous connective tissue. Muscle cells are there, epithelial cells, and those blood vessels, all of which are considered then the skeletal system or the bones themselves, right? So again, it's an organ because it has all of that. Okay. So what we're going to look at here, just a little, you know, so far is kind of looking at the structure, how we name them, how we form cartilage, how cartilage is formed. And now what we're going to look at is tissue itself. We're going to look at the gross aspect, the microscopic aspect, and the chemical aspect. Just kind of looking at some chemicals that actually are consisting of bone. Okay. All right, so looking at the gross anatomy, the kind of big aspect of it. What we're looking at here are the two types of bone that we have in our body, one being compact and the other one being spongy bone, right? Compact bone and spongy bone. Compact bone is really dense. It's an outer layer of the bone, of every bone in fact. It's the one that appears smooth, really solid, really tough. When you start to look at bones during lab, what you're going to see is those bones that are nice and long and smooth and sometimes short. But anything that you touch that's smooth on the external part of the bone is considered a compact bone, the compact portion of the bone. And spongy bone, as you look inside of a bone, so we'll see that also in lab when you see these, you know, these sections of bones split up. In the inside of the bone, you'll see this kind of honeycomb. I like to call it Swiss cheese, but a honeycomb kind of aggregation of this bone in different pieces, in different shapes and sizes, is what we consider spongy bone, right? These flat pieces of bone that make up the, you know, sponge or the Swiss cheese, or what we call trabeculae. So make sure that you know that word, right? Trabeculae. Trabeculae is a word to describe then, you know, the bone that makes up that honeycomb shape, right? Trabeculae. In between the space that we see in trabeculae, you're going to have this red or yellow bone marrow, depending on the location of where you're going to find this spongy bone. Normally with red bone marrow, but also you can have yellow bone marrow as well. And so we see this here in this figure. So we see what this looks like here. Okay, so all of this area, even here, and I'll draw kind of a exterior line here. All of this here would be considered, you know, spongy bone, right? All of this here. So they'll all be considered spongy bone itself. You can see the trabeculae there. You can see this kind of different pieces of, looks like shards of bone itself, and that would be considered spongy bone. And anything white, I'll go ahead and change the color here, but anything white, like right here in this location there, this location here, and even on the outside surface of the bone itself would be considered compact bone, the smooth portion of the exterior part of the bone. What we're looking at here, what it seems to be, is either the femur or the humerus, right? The thigh bone or the arm bone itself. Okay, so when we look at short, irregular, and flat bones, because we looked at a long bone just right now in that figure, when we look at short, irregular, and flat bones, because they have a different kind of structure, because they look differently and they're not long bones themselves, they're structured differently internally. So when we look inside of them, in fact, there's bone marrow that runs, or excuse me, trabeculae, spongy bone that runs right in between. And then sandwiched in that spongy bone is actually 2 pieces of compact bone. So you find this in the short bones. In fact, if you cut a short bone, or say a wrist bone, you cut one in half, you would see compact bone on the outside, spongy bone on the inside. You did the same thing with an irregular bone, and if you took the same thing with the flat bone. And we'll see a picture of that. Sandwiched in between would be the spongy bone. We call that spongy bone in these types of bones here, and I'll use the highlighter to highlight this. Dipole, right? That's the name we use to describe the spongy bone that is found in short, irregular, and flat bones that are sandwiched in between. Okay. Now what you see is 2 layers here, and these 2 layers are the same layers that you will actually see in a long bone in cells, but we can go ahead and talk about them here. Periosteum and the endosteum. Okay, periosteum and endosteum. Periosteum is an outside covering of compact bone. This would be the external part of the compact bone, both in all of these 3 bones, type bones here, but also in the long bone as well. And what we call the endosteum, the inside covering, the inside lining of compact bone on the inside, the internal part of the bone. Call that the endosteum. Peri means outside, endo means inside. Okay, so going to this figure 6.4, right, talks about the flat bone, what it looks like. And notice, again, to put in context here, right, the portion here, I kind of used the wrong color there to, okay, so let's say right here, this would be compact bone there, be compact bone there, right, compact bone there, sandwiched in between, change the color there, is all of your, spongy bone, your dipole, right, dipole. That dipole is sandwiched right in between this flat bone, and in fact what we're looking at is the portion of the skull, okay, which is considered a flat bone. We see that there. Okay, so let's look at the gross anatomy here. Look at, we're still on gross anatomy, excuse me, but we're going to take a look at these major anatomical names of bone themselves, right? In particular, we're looking at long bone here now. And when we're looking at long bone, we see that all long bones have a shaft. We call that shaft a diaphysis, right? Or diaphysis. Okay, that's the shaft portion of the bone. And the end of the bone is called the epiphysis. Okay, and actually there's 2 ends to the bone. This is a long bone, 2 ends of the bone. These are both be called epiphysis, right? Diaphysis or diaphysis is right in the middle. That's the shaft. And then your membranes, right? Okay. So the diaphysis, diaphysis is the shaft that forms the long axis of the bone. This is made up of compact bone. It surrounds an internal cavity that's usually filled up with yellow bone marrow, otherwise known as fat. Okay, we find that in adults. It's a little bit different when you find that in a child, because a child is kind of set up a little bit different as far as if there's yellow bone marrow or sometimes red bone marrow in place of yellow bone marrow, which changes as you grow older. And so the epiphysis is the end of the long bone. Okay, the epiphysis is the end of the long bone, and that is usually consisting of compact bone on the outside and the spongy bone on the inside. That's what you see there. And at the ends of the epiphysis, so the end of the end, the very exterior, is articular cartilage. So articular cartilage, in fact, covers the end of the epiphysis. Okay. Between the diaphysis and the epiphysis is what we call the epiphyseal line. Okay. So the epiphyseal line is a remnant. It's a leftover line that used to be are what we call the epiphyseal plates. Okay. This is left over from childhood, and in fact, long bones had a little thin piece of cartilage in between the diaphysis or diaphysis and the epiphysis. There was a long piece of cartilage that actually, when divided, which it does divide rapidly, that cartilage becomes bone, and it actually causes our bones to grow in length. Okay, which is important to have in childhood because you want to grow in length. As your bones grow longer, so does the rest of your body, and that's actually how you grow in height. And then after puberty, so through puberty, it really kicks up the notch, and then after puberty, that cartilage becomes calcified and it stops undergoing this rapid mitosis. And because it does that, we see this line left over. Okay, the old cartilage that's now actually, in fact, bone. Okay. So here's our structure of the long bone. You see the epiphysis here. You also see the epiphysis down here. And you see the diaphysis or diaphysis there, right? Again, these are the ends of the long bone, epiphysis. In the middle is a shaft. And you can see, and I'll draw a line here to represent the epiphyseal line, where that cartilage that was there at one point in childhood, it's no longer there. We see that as the epiphyseal line. Okay, just a close-up view of the section of bone there. You can see that there is the articular cartilage. So in fact, we are right on the outside edge of the epiphysis. And underneath the articular cartilage, we have, in fact, change the color here, compact bone there. Okay, and underlining that, or deeper, we have then spongy bone, right? All this right here is all spongy bone. Okay, so notice the endosteum, which is the inside lining of spongy bone and of the actual bone itself. And so we see that there as well. Okay, so we talk about membranes. So we've talked about the diaphysis, and the epiphysis, but then we talk about membranes, right? The two types of membranes that you have in long bone here is what we call the peristeum and the endosteum. Peristeum and the endosteum. Peristeum is a double-layered membrane, okay? And it covers the external surface, okay? All external surfaces except for joints, right? And so in the peristeum, you in fact have a fibrous layer, okay? An outer layer, which is a dense, irregular connective tissue, okay? And it's a tissue that we use, these fibers that we have in this dense, irregular connective tissue is called Sharpie's fiber, okay? Sharpie's fiber. So this fibrous layer is very, very fibrous, and it actually helps to bind then this layer onto the outside surface of compact bone. Okay, In that, so we have that fibrous layer, and then we also have an inner layer we call the osteogenic layer. Okay, when we use the word osteogenic, osteo means bone, genic or genic comes from the word meaning genesis, which means make. So what we're meaning to say in this word is making bone, right? So which is a really important thing to do. And in fact, we've got osteogenic stem cells. And what do stem cells usually do? Okay, will usually divide, and stem cells are a type of cell that will divide and actually turn into many different types of cells as it's dictated by the body. And in fact, osteogenic stem cells can actually turn into all different types of bone cells. And we'll take a look at what we mean by bone cells. But osteogenic cells are found there in that peristeum that actually can turn to many different types of bone cells. So we've got many different nerve fibers, right? Blood vessels are found there. Nerve fibers are found there. And they go through these areas internally inside the bone through what we call nutrient foramens, little openings in the bone where the blood vessel and the nerve enter into. All right. All right. So the endosteum is actually the inside lining of the bone tissue, right? Bones themselves. Okay. So it's a membrane, right? It covers the trabeculae, covers the inside cavity of the yellow bone marrow. So we see that there. And so see that layer as well. So in this figure here, you can see then the structure of the long bone, showing the two layers, right? The endosteum and the periosteum. Okay, the outside layer and the inside layer. Okay, so we do have tissue in bone. We have hematopoietic tissue, which is tissue that actually is found that actually participates in bone cell production. Okay, so red bone marrow, we find that in trabecular cavities in the spongy bone. When we take a look at a flat bone, we see it in the diapole, right? Dipole is that word that we use for flat bones, right? The spongy bone that's in between the two compact bones, right? And this type of red bone marrow has stem cells that produce all types of blood cells that we have in our body. Your red blood cells, your white blood cells, your types of white blood cells we call lymphocytes. All of these actually form in the red bone marrow. Okay. Now, in adults, red bone marrow is located in the head of femur, humerus, some flat bones, things like that. In children and newborns, in fact, the medullary cavity where you would have usually yellow bone marrow is where you're going to have red bone marrow as well. So you'll see that also. Okay, and so when we look at outside bones, we notice that there is what we call bone markings. Okay, little places that you find in bones that are usually, they look like little irregularities in bone on the outside surface, but this is actually where we have sites of attachment. What do we attach to bone? Well, we know for a fact, that we attach muscle there to bone, ligaments, right? Tendons get attached to bone on the external surface, and that creates movement, as I mentioned, right? And so there's three types of bone markings. You're going to be asked to know all three types. Okay, not necessarily all of the bone markings, but the three types, because we'll talk about bone markings in lab, and you'll get to know, you'll be very familiar with all the bone markings of bone. So there's going to be a lot of them, but you'll study those. But you'll need to know the three types, right? A projection is a bulge in the bone, and it's outward, in fact, outward projection. Okay, an extra outpouring of bone, and we call that a projection. Okay, a depression is a groove or a bowl shape. Okay, and so you see that as well. And an opening of bone is like a hole in the bone, canal of the bone, where things go through as well. So you'll see both of which, or all three of which, in bones as we study them in lab, for example. This table I decided to put on here just to show you that there is different types of those bone surface markings, and you can see them. There are many different names for each one of them, and you can see them on this table. Okay. All right. So let's talk about the cells of bone tissue. There's 5 major cells of bone tissue. They're listed for you here. We'll talk about each one of them, and we'll talk about why they're important for bones and for not only bone development but bone regulation as well. So we'll talk about each one of those here. Okay, so our first one is the osteogenic cell. Okay, and so we just talked about an osteogenic cell, an osteogenic stem cell, and these are actually what these are. They fall into this group. We sometimes call them the osteoprogenitor cells because they actually are the ones that undergo mitosis. They're stem cells. You find those in the peristeum and the endostem. When they're stimulated to undergo cell division, they will actually undergo cell division, and they will turn into many different types of those other lists there of those cells, and especially osteoblasts and bone lining cells, both of which are really important for the maintaining of bone tissue, and we'll see that there. Now, some of them turn into those, and then there's some that are reserved that stay as stem cells for the next time they get stimulated. Osteoblasts. Okay, so when you think of blast, you think of making. Okay, so whenever you hear a blast, it's usually a bone, usually a forming cell. It's doing something, it's building something. And in fact, osteoblasts are bone forming cells. Okay, so they form bone, and what they do is they secrete this matrix that's unmineralized. Make sure that you keep an eye on that word, unmineralized. It does not have minerals to it. It's just the matrix, be like concrete pouring on a foundation. We call that osteoid. Okay, that's the matrix that gets made and secreted by this bone forming cells, right? These osteoblasts. Okay, so this matrix is basically made up of just collagen and these proteins that bind calcium. So again, we're laying the foundation to add, for example, calcium in here as well, right? Most of the proteins that you find that are calcium binding is the collagen. So it's made up of basically the collagen there and then those calcium binding proteins, right? Okay, here you can see a osteoprogenitor cell. Now you won't see these as far as on the test per se, but you can see that how they look a little bit different. Here's your osteoprogenitor cell, and there's your osteoblast. Here's your osteocyte. Okay, so this is a mature bone cell. This one does not divide whatsoever. Okay, they lie in what we call lacunae, and we'll see that in just a second. We'll see what that means here in just a second. But lacunae, they lie in lacunae. They no longer divide. Okay, what they do is they act as maintainers. They maintain the bone matrix, that osteoid there, right? They act as stress or strain sensors. So when we have a stress in a bone or strain in a bone, these cells will recognize that. They will be sensitive to it. They'll recognize that area. And so any kind of stress on the bone. Now, when we talk about stress, we think more negatively, stress and strain, but this is a natural occurrence. When we apply force from our weights, from our movement, from different types of movement, creating force on the bone, there's certain parts of the bone that feel the actual stress, right? Stress points. Osteocytes respond to those stress sites. They understand that this part of the bone is feeling more stress than another area. And what they do is they communicate with osteoblasts and osteoclasts to help build more bone in that area, to basically reinforce that area because of the extra stress. And so when we look at, for example, weightlifting is a really important endeavor when it's a health benefit of lifting, for example, using lifting, weights per se. Not necessarily weights in a gym, although you can do that, but actually using your muscles in a certain way for, hobbies, tasks, chores, things like that. That's really important because it actually helps your bones strengthen And the way it does this is because the osteocytes respond to the stress of the bones from the muscles pulling against it and from that force, and then will respond by adding more bone to certain areas and then increasing the strength of the bone, so that, for example, if you do have a trauma, your bones are much stronger. So it's actually a really important thing, right? Bone lining cells, right? Flat, as in, they look flat. They also help, we think, help protect the matrix, maintain the matrix as well. They actually help to kind of smooth everything out, to maintain it, to make sure that everything's growing correctly, that the other cells are actually undergoing their job, right? And osteoclasts, all right? So the way I think about this is if osteoblasts build bone, osteoclasts actually break down. Okay, so we call this breakdown of bone, and I'll highlight this for you. We call this breakdown of bone. The term bone resorption. Bone resorption is actually the breakdown of bone. Okay, so these osteoclasts have these ruffled borders. You're going to see the picture here in just a second. You'll look at the cell and see these kind of look like little fingers, if you will, at the end of the cell. And what they do is actually secrete an enzyme that actually, eats away at bone, surface of the bone. And that's really important thing to actually look at, because when you look at bone itself, we're actually degrading bone microscopically and adding bone in places. We're actually remodeling bone every single part of our life, which is an important thing to do, because as you replace it with new cells and new calcium, and make it again, reinforce it, make it stronger, and to continue to make it stronger. So that's a really important thing. So osteoclasts are just as important as osteoblasts, really are. And again, the key word is remodeling bone, and they help do that. Just to show you, there's your osteoblasts on the left, your osteocytes on the right, and of course here is your osteoclast. You see this ruffled border here that actually are found on the surface of bone, and they actually secrete the enzyme that breaks down bone. Okay, so here's your typical osteoclast. You see the bone matrix there, all surrounding this area. Okay, here is your lacunae, this area here. Okay, and then this brown, I'm sorry, not brown area, but this kind of dark gray area would be then this right here would be your osteocyte. So three major areas, right? The matrix, the osteocyte inside, and the lacunae surrounding the osteocytes. If you notice this, and if you look really close, you can actually see, I'll erase this so you can see that a little bit better. Here is your osteoclast, right? There it is. And there's your ruffled border, right? Here's your actual osteoclast there, right? Okay. And here's your ruffled border. This is the area where it's actually on the surface of bone, secreting that enzyme that actually helps break down this bone tissue. So it's actually doing its job. It's actually, right on the surface of the bone, secreting the enzyme that's helping break down. Okay, so we call compact bone, but we also call that laminar bone. It's the word we use to describe laminar bone. Okay, consists of osteons, canals and caniculi, and interstitial and circumferential laminae. Okay, all of which we're going to discuss here. All right, our osteon is called the osteon, or otherwise known as the Haversin system. Okay, an osteon is one structural unit of compact bone. Just one structural unit. Okay, one structural unit of compact bone. and that's one osteon. Okay. Now, several osteons together, in fact, make up compact bone itself. So many osteons put together make up compact bone. It's one osteon is considered is consisting of one elongated cylinder, one long cylinder. Okay, runs the parallel to the long axis of the bone. So wherever you see a long axis, for example, I'm just taking my forearm here. If I take this forearm and go all the way down, this would be the long axis. So those cylinders, these cylinders here would actually be running up and down through the long axis. So they're not running this way on the bone, they're actually running up and down. That's what you see there. Okay. Very much made like a pillar, right? And this pillar bears weight. So as you put weight on top of my fist, those bones and those osteons are holding everything up and can actually hold a tremendous amount of weight. When you look at the femurs, the largest bones in our body that actually are thick and actually hold up the most of our weight of our body, tremendous amount of weight for this bone itself. So these pillars actually are engineered, they're designed to hold a lot of weight. Okay. Each of those cylinders have several rings, and we call those laminae. Okay, like lamination, right? Coverings. Okay, these rings are actually rings inside rings inside rings, and we're going to see those in a second. We call those laminae. Okay, laminae has collagen fibers that run in different directions. So you'll see these lines in just a second. I'll show you the collagen fibers and how they run in different directions that make up these rings that we call, laminae, right? So here's your osteon, just one osteon itself. And if you notice, there's actually 3 rings here, one internal, one middle, and then one external. And you can see these rings that are made up of compact bone, or compact bone is made up of these rings. And you can see these little lines. You'll see these little lines kind of running this way, but these are the collagen fibers. Notice that the lines run here on the external ring, right? And you can see this running this way, right? A different direction, yeah? So a different direction than the outside ring. And then again, you see a different direction of these running in this direction, okay? So different directions, one running to one way, one running the other way, and that actually helps to strengthen this pillar, if you will, this laminae, and the bone overall. Okay. Okay. So let's take a look at canals and caniculi. Right. Canals and caniculi are actually little connections, if you will, inside of this this laminae that we see here. Right. And so when we look at a central canal, what we call a Haversing canal, this canal actually runs through one osteon. And what runs through this osteon? We've got blood vessels and nerve fibers running through each one of those osteons. And we'll see how many actually, when we look at the figure here shortly, we'll see how big, this area is, because many osteons put together actually become the compact bone. So we've got this one canal running through the entire osteon that has the blood vessels and nerve fibers. And then directly adjacent from those, there's these, basically canals that are interconnecting the central canals to other central canals through these little small canals we call Volkmann's canals. And those canals occur at right angles to the central canal. So they're interesting because they connect blood vessel to blood vessel, nerve to nerve, all throughout the osteon system here. And we're going to see all of this. We'll see the figure that puts it all together here. Okay, we mentioned lacunae, or I mentioned lacunae there. There's little cavities that have the osteocytes, right? The osteocytes, bone lining cells. And so these cells, in fact, are found in these little cavities intermingled between all the laminae themselves. And so what are caniculi? Caniculi are these little smaller canals that connect all the lacunae together, and to the central canal. They look very much like a spider, if you will, and so I'll show you those as well. But they connect all of them together. Okay. So what do we use these for before I kind of go on? They allow the canicular communication channels between all the osteocytes, the lacunae that have the osteocytes of every single osteon there that make up the compact bone. And they actually let nutrients go into those cells because those are living, osteocytes are living cells, and waste because that's a side product of these cells, undergoing their job. They have waste, and the caniculi help to actually take that away and bring nutrients from cell to cell. Okay, before we get into that figure, the last part of the presentation here, I want to talk about what's interstitial versus circumferential laminae. Interstitial laminae are actually laminae that are not part of the osteon, but they fill the gaps between the osteon. Okay, so if you took cylinder and cylinder together, okay, so if I was to draw this, for example, all right, so what I'm going to do is draw a little square here. Hopefully I do this right, okay, and I see one osteon. Say I connect it, pardon me, there, right, okay, and that's one osteon. Let's say I drew one ring after another ring after one more ring. This would be our osteon. Let's say it's a crosscut. We've cut it and we're looking kind of, top down or sideways, and we're looking at the laminae there, right? The osteon, if you will. Well, if you'll notice that, and I'll go ahead and use the highlighter to highlight this area here, all here, there, all there, even here, and there. You are there, in fact, see that there are spaces in between the osteon and the square. This space, in fact, is where we have interstitial laminae. The laminae that do not make the rings, but they fill the spaces or the gaps between one osteon and the other one. The space that's filled in between is what we call interstitial laminae. And the circumferential laminae, these extend beyond the entire surface of the diaphysis. So we see these are surrounding the entire compact bone themselves. So they're a big, big version of this here. Okay. So finally, to the figure here, and looking at this, we see a couple different things here. So I want to point out, and I know it's a small figure, but I want to point out the one osteon. So they took one osteon here, noted by the arrow there, and they took one osteon, they pulled it out, so you can see it's ring within a ring within a ring. We notice at the middle of the ring, right there, on the tip of the arrow, you find the central canal. That's where the blood vessels will run through. And then what they've done on the right side is actually cut some of the osteons in half. Okay, and I'll use this blue pin here, kind of cut the osteons in half so that way you can see how the central canal runs longitudinally all the way down, each side of the long axis of the bone there. You'll notice that, in fact, there are a bunch of osteons put together, and you'll notice, and I want to kind of show you, and I know this might be hard to see, so I apologize if it is, but you'll notice, for example, see if I can use this here, right here in between this area here.
Did you accidentally summon me?
Right here, you'll actually see right in between those four osteons is a space that we would fill up with laminae there, right? Interstitial laminae. Fills the gap between osteons. And surrounding the entire osteons, if I extend down this way, would be circumferential laminae. And you can see that there, right? Surrounding the entire set of osteons there. That's circumferential laminae, okay? Finally, if you look down here really quick, okay, you'll notice these small little gaps here we call lacunae. I'll kind of highlight one of them there. There's a couple different ones, and you'll see these kind of lines that kind of form out this way. And in between each of the rings there, we would call those their caniculi that extend or connect every single lacunae, which are kind of this, it looks like a spider, the lacunae and the caniculi, and you can see that. Okay, let's talk about spongy bone here, right? Spongy bone is really looks poorly organized because it actually looks like a random kind of set of different shards of bone here that make up spongy bone, but they're actually organized based on the lines of stress. Based on the stress of the bone on the either end of the bone where you usually find spongy bone, you'll have then a trabeculae, a little shard of bone there. So it actually helps resist stress there. So we change them depending on the stress level. And that's kind of where you see most of these kind of spongy hole shape where the trabeculae are, right? This is an easy, actually really easy way to think about it, right? Trabeculae are like cables on a suspension bridge. So they actually hold up things, right? Hold it, right? Hold it in place. And that's kind of what the trabeculae, the Swiss cheese, spongy kind of tissue that makes up spongy bone, this is what it does there. Okay, so you can see those there, right? This box, right? You'll see that. There's all your trabeculae, and notice that they're different hole shapes, hole diameters. You'll see that the bone is in different shapes. Some are thick, some are thin. Again, these are lines of stress that the body's feeling here. Okay. So lastly, let's take a look at the organic components and the inorganic components, the chemical component, right? This is the chemical side of bone tissue, okay? When we talk about the organic components, anytime we use the word organic in chemistry, we're usually discussing molecules that are made up of carbon and hydrogen, okay? And other things as well, but they must have carbon and hydrogen to be considered organic. And we consider, for example, all those cells are organic molecules, right? Those living cells are made up of organic molecules, and because they're made up of organic molecules, these are the components that are organic, right? All right. The osteoid, right? The osteoid is also the matrix, right? That is basically bone tissue, and that's organic as well. And of course, we've got these collagen molecules, right? Okay. We have these bonds between these organic molecules that we call sacrificial bonds, and these actually help displace energy and actually help with the stress of the bone as well. Okay, and so let's talk about the organic components. We use this word here, hydroxyapatites, right? We call these mineral salts. 65% of the bone, mass of the bone is made up of these hydroxyapatites, one of which is made up of calcium, right, and of phosphorus. Those two minerals put together in a chemical bond we call hydroxyapatates. These are the mineral salts that that make up bone and make what bone is a hard substance, right? They are in and around collagen, and that's actually what makes up most of the hardness and the resistance to compression features of bone. That's what we see there. Okay. So a couple facts before we end this this PowerPoint, right? Bone is half as strong as steel, right? In resisting compression, which means compressing means sandwiching, right? Okay. But strong as steel in resisting tension, right? Tension. So tension is actually not compression, but sometimes stretching, okay? Sometimes stretching. And sometimes bending, right? That's tension as well. So when we bend something or we stretch something, bones are actually as strong as steel. Strong as steel. You know, that is pretty amazing to actually think about, right? But as far as compression, half as strong as steel. So we see a lot of compression fractures, for example, in the body, but we also see, you know, bending. But just to keep in context, you know, even bending, that's a tremendous amount of force applied to cause a bone to break. So that goes to show you what kind of stress is involved in breaking bones that way. So the inorganic components, even in fact, in bone overall, last long beyond death. So even that's how strong and resilient they are, because bones can last long after tissue is gone, everything is gone, bones remain. Even bones remain for millions of years. I mean, we look at dinosaurs, and dinosaurs, you know, millions and millions and tens of millions, hundreds of millions of years ago, they're still in the ground. And it goes to show you how resilient this, you know, inorganic components that are added with these living tissues, how strong they can be, how long and resilient they can be. All right, folks, I hope you enjoy this. I hope this helped you as far as this chapter is concerned, at least looking at bone tissue. So I appreciate your feedback. I'm going to post this on Canvas. I'm also going to post this on YouTube, so I will have this out. I hope this helps you, and let me know if it does. I appreciate your feedback. What can I do to improve these types of presentations? Again, this is only my, you know, just to let you know, it's only my second time of actually recording these. Yesterday was my first, last night was my first, this is my second. So I think as I'm going around, as I'm doing this more and more, and going around and recording myself, I think I'm getting better and better. So, but there's always room for improvement, but I need your help in doing that. So once you go through this, if you have any comments towards that, I would really appreciate it. All right. Thanks.